Hey, it is Mr. Shrum back again with some physical science tutorials. And today we're going to look at graphing motion. Last time we were describing motion, measuring it, and now we're going to graph those measurements. Let's get into the objective. We'll analyze, interpret, and then construct graphs that track all of this information, such as displacement, velocity, and acceleration over time. So let's get into the content. Let's go. So for the introduction, look around you and you'll see that objects moving about you exhibit all types of motion. In this example, think about an ice hockey game. Picture the puck as it glides along a straight line path without slowing down on the ice until someone or something interferes with it. Or consider this: while you and a friend are driving to your favorite restaurant, you suddenly spot a deer in the road. Your friend firmly puts on the brakes and manages to stop the car without swerving out of the way. Although both of these motions happen in a straight line, there is a difference. While the puck displays uniform motion, and uniform motion means it travels with almost no change in velocity, the car demonstrates accelerated motion, meaning that the velocity is changing. Think about what these motions would look like if they were on a graph instead. So let's look at what those would look like. Talk about graphs and velocity first. Physics deals with two types of quantities. We have scalar and vector. Scalar quantities such as speed, mass, distance, and time are all described only in terms of their magnitude, like how big they are or how fast things are going. While vectors such as displacement, velocity, force, and acceleration, they're described in terms of magnitude plus a direction. So they're this big and they're going in that direction. So that's what a vector can tell you. Speed and velocity are two common quantities that we measure when we're studying motion. Speed is the scalar measure of how fast an object travels. It is the rate at which an object covers a certain distance over a period of time. But because there's no direction, it's only scalar. And here's the formula for that. We have speed equals distance divided by time. So you'll have miles per hour, for example. And that's your speed, how fast a car is going. On this speedometer, you can see that. While velocity is a measure of how fast an object travels, plus a direction. So to calculate velocity, we consider both distance and displacement. Displacement is the change in the position of an object and considers both distance and direction. So it's defined as the displacement divided by time. So distance for speed, displacement for velocity. And on a graph, if we're putting displacement on one axis versus time on the other, this is how it would look like. While studying velocity, we consider two variables, displacement and time. And variables represent factors that can be measured to understand an event. Independent variables are factors that either are not influenced by other variables or can be directly controlled or manipulated. And an example of an independent variable is time. It progresses independently no matter what else is happening in a situation. Time is always going. To study velocity, we can observe how much the displacement has changed over a period of time. So in this example, time is an independent variable. Dependent variables are factors that depend on the values of other variables, but you can't directly control the dependent variables. That's not why you should be having an experiment. Dependent variables change, or they don't change, based on the values of independent variables. So we might observe displacement in a certain situation over time. So in this case, displacement is a dependent variable. Independent variables are always plotted along the x-axis. So along this x-axis. Dependent variables are plotted along the y-axis. So in this displacement versus time, time is plotted along this x-axis. Displacement is plotted along the y-axis. Let's see what we can learn from a displacement versus time graph. Consider an object moving in the positive x direction with a constant velocity of 5 meters per second. So we see that the object's position, x, is at the point marked 0 meters. When the time equals 0, the initial position is equal to 0. This figure shows a representation of the object's motion. The shape and slope of the line on the graph represents the type of motion. The straight line graph indicates that the object is in uniform motion, meaning the velocity is the same. Positive slope, straight line, constant velocity. The ice hockey puck is a good example of this. A positive slope means that the velocity is constant and positive. Using the values for position and the corresponding time intervals, we can calculate the average velocity of the object. And we can see how in the next slide. The average velocity is the total displacement or change in position of an object divided by the total time. So, in other words, the slope of the line is the average velocity. Slope equals average velocity, which equals the displacement over time. So you can take the change in displacement divided by the change in time between any 2 points. Remember that delta, this triangle, means change. Here's the change in displacement over the change in time. The average velocity of the object discussed on the previous screen is 10 meters minus 5 meters divided by 2 seconds minus 1 second. So it's taking this point and this point. Okay, and subtracting this one from that one. So that leaves us with 5 meters over 1 second, or a positive 5 meters per second. And this positive is important to include with velocity because it's a vector. Vectors need a magnitude and a direction, positive or negative. So that was a an object with a straight, uniform velocity. However, not all objects are like that. If it has a curved line like this, our line will look not straight. So the slope is still positive, it's still moving up. However, it's not as easy as the previous answer. You can use the slope of this graph to determine the average velocity, just like we did last time. But because it's not uniform, because this line is not straight, the average velocity during different time intervals will be different. So this is the average. Sometimes the object will be going faster than this, and then sometimes it's also slower. So the average is in between the highest velocity and the lowest velocity. So using that average formula from the last page, choose 2 points. So we'll choose this one and this one. Or we'll do t equals 1 and then t equals 0. That makes it easy. 1 minus 0 over 1 minus 0 leaves us with 1 meter over 1 second, and that's a positive 1 meter per second. And you'd get that if you picked any two average velocities. Yeah. In a displacement versus time graph, what does the slope of a line at any point indicate? Velocity. Tangent and secant lines. The slope of a displacement versus time graph tells us the average velocity of an object between two defined points on that line. The average velocity is the change in the position of the object in a given time interval. But during this time interval, the object may have sped up, slowed down, or stopped. In other words, the very instantaneous velocity, or the velocity at a very particular instant of time, might keep changing. So if you look at this graph, the secant line in red joins 2 points on the curved line. That gives the average velocity of the object between those 2 points. So that is the average velocity. And the tangent line in black touches only 1 point on the curved line and represents the velocity of an object at that particular instant. So you can take any 1 point along the line and draw a line that only touches the graph at 1 point, and that will be different at each point. That tangent line will appear different. So sometimes the average velocity is not the most accurate thing to, it doesn't tell you as much information as you need sometimes. Here's a video. In many physical situations, quantities such as position, velocity, acceleration, force, and energy change over time. And in most of these cases, looking at an average change over a long period of time, it's just not as useful compared to looking at instantaneous values for very specific times. So this video here applies it to a real life situation. See how instantaneous velocity and instantaneous acceleration might be measured and calculated for a car in motion. You don't need the sound to look at this, but you see at certain points, the tangent line would be different. And then once it completely stops, it forms that flat line. So here they're drawing the tangent lines. Calculating the average speed. But then you have the values themselves at instant points. And then it talks about how once you get those speeds at specific instances, then you can graph those on a speed versus time graph. And then you take the slope from that, the change in speed over the change in time, or the change in velocity over the change in time, and then you get acceleration. So this all starts to come together once you think of it in a certain way. Is it another activity you can do? And then, yeah, getting into acceleration graphs. What can we, or how can we use graphs to find acceleration? In this example, when you start a car, it's initially at rest. So velocity equals 0. And if you step on that gas pedal, the car begins to move forward and its velocity increases. When you press the brake pedal, the car slows down and the velocity decreases. A change in velocity over a period of time is known as acceleration. Note that slowing down is acceleration, but in the opposite direction. But in everyday speech, we call it decelerating. And that's, I guess, not the greatest word to use because you're just accelerating in the opposite direction. So you were going forward, but now as you brake, your acceleration shoots back in the opposite direction and you slowly come to a stop, or quickly, depending on how quickly you brake. But here you see the formula, change in velocity over change in time, delta V over delta T. Delta means change. The velocity versus time graph. Now let's see how we can represent the acceleration of an object. So if you plot the velocity in the y-axis and time in the x-axis, that slope equals the acceleration. Change in velocity divided by the change in time gives you the slope. So the independent variable would be the x-axis, the time, and dependent variable on the y-axis, velocity. So whether the type of line is straight or curved indicates the type of acceleration. If it has constant acceleration, then it will have a straight line. If a line has a positive slope, the acceleration is positive. If it has a negative slope, the acceleration is negative. So let's see how we can determine that. So velocity is 0 at time 0. And then if velocity is 5 meters per second, graph that. And then plug it into the formula to find the average acceleration. Change in velocity over change in time. Pick 2 points. Pick 1 and 2. Plug in those numbers. 10 minus 5 equals 5 meters per second. 2 seconds minus 1 second divided by 1 second equals positive 5 meters per second, or positive 5 meters per second squared, whatever you prefer to say. But acceleration is a vector, so it needs a direction. Remember. Now let's look at a velocity versus time graph that has a curved line. That means this acceleration is changing at each instant. An upward slope means it's accelerating in the positive direction. So you can calculate the average, like we calculated the average velocity too. Plug in any 2 points. And in this one, we get positive 1 meters per second between time 0 and time 1 second. You have another activity here that you can do. In a velocity versus time graph, what does the slope at any one point indicate? It indicates acceleration. Finding area on a velocity versus time graph. Now you know how to use a velocity versus time graph to determine acceleration. You can also use this to find displacement. So in this velocity versus time graph, if you find the area underneath, that equals the displacement. So in other words, displacement equals velocity times time. And that makes sense if you look at the units. So we have 15 meters per second times 3 seconds. So if you're going 15 meters per second for 3 seconds, you're covering 45 meters, given that velocity is constant right here, right? That's why the graph looks like this. And you can think of that as a rectangle, right? Time equals 3 seconds times velocity equals 15 meters per second. We just figured out the displacement for a basic constant velocity. That same area method can be used to find displacement in more complex situations too. So for this graph, the velocity of the object is decreasing over time. And we want to find the displacement after 5 seconds, after it comes to a complete stop. So you can see this triangle here, right? And we can use that to find the area. The area of a triangle is 1/2 the width times the height. So we have 1/2 times 5 seconds times 50 meters per second. And that equals 125 meters. So the units cancel out seconds with seconds. So we have 125 meters as displacement. And you can also further break it down. Whatever makes it easier for you. This is a trapezoid. And if you remember the equation for a trapezoid, this is it. But you can also break this into 2 other shapes. So right here, you can pretend that's a square or a rectangle, right where that becomes a triangle. And add the area of a square or rectangle plus the area of a triangle. If that's easier for you to think about, go ahead and do that. So as you can see, graphs have a lot of information. You can read data points directly from graphs. The slope tells you if a variable is increasing or decreasing. A change in slope tells you even more about what's happening with the variable. And then you can use the area under the graph to determine other values too. Predicting graph shapes. So these start out with one shape, and then it wants you to draw the velocity and the acceleration versus time graphs. And so here's the answers. It looks like this object is moving positive direction, but it's also moving more at a gradually increasing rate. So the slope is getting higher and higher at a pretty constant rate. So that means the velocity is increasing at a constant rate and would be a straight line. The slope is getting more and more positive. So that means this is what the velocity versus time graph would look like. And since the slope is constant here for velocity versus time, that means acceleration is constant. So we get that flat line. Whereas this one, an object is still going, but then it slows down. So velocity increases for a while, constantly, but then it flattens out. So the slope approaches zero and then stops. So here, that means the velocity versus time graph, there was constant velocity right there. And it wasn't increasing or decreasing, but then it started decreasing pretty rapidly. So constant decrease in velocity. And that means this graph doesn't really make sense right here, but just ignore that zero. That means here the acceleration was zero because there is no slope. There is no change in y over x. There's no change in velocity, so acceleration equals zero right here. But then the velocity changes negatively. And so this graph should have a negative number. It should be acceleration is zero, and then acceleration is actually negative. So this should be a positive or a zero, a flat zero, and then it would drop to a flat like negative number too. So be careful. Remember what each graph is trying to tell you and what information you can pull from the graph. There are two types of motion that we described earlier, the hockey puck and the brakes in the car. So that one would be hockey, and that one would be the car braking. And these are the velocity and velocity versus time. This was displacement, now this is velocity. positive velocity. And then we have decreasing velocity, increasing velocity, decreasing velocity. So the slope of this would be a positive acceleration. A negative slope here would mean a negative acceleration, accelerating in the opposite direction. So cool. Well, that's all I have for you today. Thank you guys. I hope that helped clear some things up, and I will see you guys later.